Chapter 9, Module 3. In this module, we shall apply the properties of the induced homomorphisms to get various important results. Among these, the first one is to establish that a homeomorphism always induces an isomorphism between the homology groups. Recall that the induced homomorphisms have the following properties. For each n greater than equal to 0, if I is the identity map, then Hni from Hnx to Hnx is the identity homomorphism, and if f and g are two continuous functions, then Hn g composed f is equal to Hn g composed Hnf. Applying these properties, as in case of simplicial homology, we obtain that a homeomorphism F always induces an isomorphism between the homology groups. That is, if f is a function from x to y and it is known that the function is a homeomorphism, then Hnf from Hnx to Hny, the induced homomorphism, will become an isomorphism. Let us look at the proof of this theorem. Since f is a homeomorphism, there exists a continuous function g from y to x such that g composed f is identity on x and f composed g is the identity on y. Hence, for each n belonging to integers, Hn g composed Hnf is equal to Hn g composed f, which is equal to Hn Ix, and that is equal to I of Hnx. The first one, that Hn g composed Hnf is equal to Hn g composed f, is a property of the induced homomorphism, and secondly, replacing g composed f by Ix, we get Hn g composed f is equal to Hn Ix, and thirdly, Hn Ix is equal to I Hnx once again by the functorial property. Similarly, if we take Hn f composed Hn g, that will be equal to Hn f composed g, and that is equal to Hn identity on y, and of course, that is equal to identity on Hny. This shows that the homomorphism Hnf for every n is invertible. That is, Hnf is an isomorphism. If f is a homeomorphism from a topological space X to Y, then by the definition of homeomorphism, we know that there exists a continuous function g such that g composed f is identity on x. Now, the last result gave us that this equality will be preserved if the diagram is shifted to a diagram inside the homology groups. Now, the question is, if we replace this equality by homotopy, then what happens to the induced homomorphisms? We shall explore this now. In what follows, we use the following notations. ID will stand for the identity function from the closed interval 0 1 to itself. Gn is an element of Cn delta n cross I, which is defined by Gn equal to E1 minus E0, where E0 and E1 are the singular n simplexes defined as E0 z equal to z0, that means we are plugging in 0 in the last coordinate, and E1 z is equal to z1, that means we are plugging in 1 in the last coordinate for every n greater than equal to 0. Note that for simplicity of the notations, we use E0 and E1 for each n greater than equal to 0. Now, if we take the collection Cnx delta n and take the collection Cny del n, then these two collections will always denote the chain complexes corresponding to the topological spaces x and y respectively. Now, let us state a couple of lemma. The first lemma is a bit technical one. For each n greater than equal to 0, it can be shown that there exists alpha n from delta n plus 1 to delta n cross I, such that when n is greater than 0, delta n plus 1 alpha n plus summation j equal to 0 to n minus 1 to the power of j dj times identity composed alpha n minus 1 is equal to g n. And when n equal to 0, then delta 1 of alpha 0 is equal to g 0. With the help of this lemma, we can prove the second lemma, that if f and g are two continuous maps from x into y which are homotopic, then there exists a family of functions from Cnx to Cn plus 1 y for n greater than equal to 0. This family consists of homomorphisms such that for each n greater than 0, delta n plus 1 phi n plus phi n minus 1 delta n is equal to Cng minus Cnf. And if we take n equal to 0, then delta 1 phi 0 will be equal to C0g minus C0f. Let us look at this diagram. We are having two chain complexes. One is for the topological space x and the other is for the topological space y. This lemma says that there exists a family of functions which are denoted by the diagonal arrows in this diagram. The arrow from Cnx to Cn plus 1 y is denoted by phi n, and an arrow from Cn minus 1 x to Cn y denoted by phi n minus 1. If we look at the right triangle, then we will get a function by composing phi n minus 1 with delta n. It is a function from Cnx to Cny. Similarly, if we look at the left triangle, then composing delta n plus 1 with phi n, we get a function from Cnx to Cny. The lemma claims that the sum of these two functions from Cnx to Cny will be equal to Cng minus Cnf. Also, when n is taken as 0, then the right hand triangle is nothing but the trivial homomorphisms. So, we will get that delta 1 composed phi 0 is equal to the difference of the functions CNG minus CNF from C0x to C0y. Let us try to prove this lemma. Suppose capital F is a homotopy from F to G. If sigma is an element from Snx, that is a generator of Cnx, then sigma times identity is a function from delta n cross I to x cross I, and this is a continuous function. In view of the previous lemma, there is some alpha n from delta n plus 1 to delta n cross I, such that for n greater than 0, delta n plus 1 alpha n plus summation j equal to 0 to n minus 1 to the power of j dj cross identity composed alpha n minus 1 is equal to Gn, and for n equal to 0, delta 1 alpha 0 is equal to G0. So, for every n greater than equal to 0, we have the following composite map in Cn plus 1 y. The map is capital F composed sigma times identity composed alpha n. So, for each n greater than equal to 0, we can define a function phi n from Cnx to Cn plus 1 y given by phi n on any generator sigma is equal to f composed sigma times identity composed alpha n. And we extend this function by linearity on the whole of Cnx. Each phi n is indeed a homomorphism. We claim that such a sequence satisfies the desired condition. If n is greater than 0 for any sigma belonging to Snx, we start with del n plus 1 phi n plus phi n minus 1 delta n operating on sigma, and that will give us delta n plus 1 f composed sigma composed identity composed alpha n plus f composed delta n sigma times identity composed alpha n minus 1, and that is equal to summation j equal to 0 to n plus 1 minus 1 to the power of j of f composed sigma times identity composed alpha n composed dj plus summation j is equal to 0 to n minus 1 to the power of j f composed sigma composed dj cross identity composed alpha n minus 1, and that is equal to f composed sigma times identity composed summation minus 1 to the power of j alpha n composed dj plus summation minus 1 to the power of j dj times identity composed alpha n minus 1. But that is equal to f composed sigma times identity composed whatever written inside the bracket is actually G n. But G n is E 1 minus E 0. So, we have f composed sigma times identity composed E 1 minus f composed sigma times identity composed E 0. Similarly, if we take n equal to 0, then for any sigma belonging to S0x, we have del 1 composed phi 0 operating on sigma is equal to f composed sigma times identity composed G 0. So, for any z belonging to delta n, where n is greater than equal to 0, we then have f of sigma z 1 minus f of sigma z 0 is equal to g of sigma z minus f of sigma z, so that for n greater than 0, del n plus 1 phi n plus phi n minus 1 delta n operating on sigma will be ultimately equal to g composed sigma of z minus f composed sigma of z. And for n equal to 0, del 1 phi 0 sigma will be ultimately g composed sigma on z minus f composed sigma on z. That is, del 1 of phi 0 sigma is equal to C 0 g minus C 0 f, whereas for n greater than 0, the expression will be C n g minus C n f as desired. Now, we define chain homotopy. Suppose we are given two chain complexes, one is C n delta n and the other one is d n del n. And suppose we are given the chain maps phi n and psi n from C n to d n. Then a family of homomorphisms phi n from C n to d n plus 1 is called a chain homotopy between phi and psi if we have this expression to hold, that is, del n plus 1 phi n plus phi n minus 1 delta n is equal to psi n minus phi n for all n greater than 0, and del 1 phi 0 is equal to psi 0 minus phi 0. The lemma that we have proved here says that any two homotopic maps induces chain homotopy between chain complexes. We shall now see that this particular concept of chain homotopy, as we have already mentioned, in view of this definition of chain homotopy, we may restate the last lemma that two homotopic chain maps induce a chain homotopy between the given chain complexes. So, we have the very important result that homology respects homotopy. That means, if f and g are two continuous functions such that f is homotopic to g, then the corresponding homomorphisms h n f and h n g, they are equal for every n greater than equal to 0. To prove this result, let us start with two homotopic maps f and g. Then there exists a chain homotopy phi n from C n x to C n plus 1 y for n greater than equal to 0. Now, if we take C from C 0 x, then C 0 g minus C 0 f operated on C will give us del 1 phi 0 operating on C, and that is definitely a member of image of delta 1, which is equal to B 0 y. Hence, H 0 g of C plus B 0 x is equal to C 0 g C plus B 0 y, and that is equal to C 0 f C plus B 0 y, which is equal to H 0 f operating on C plus B 0 x for any C belonging to C 0 x. Therefore, H 0 g is equal to H 0 f. Now, if n is greater than 0 and we choose any z from Znx, that is kernel of delta n, then Cngz minus Cnfz is equal to the expression del n plus 1 composed phi n operating on z plus phi n minus 1 composed delta n operating on z, and that is equal to del n plus 1 phi n z plus phi n minus 1 of 0. Since z is in kernel of delta n, del n z is equal to 0, and therefore, this whole thing is equal to del n plus 1 phi n z, proving that a member of image delta n plus 1. Hence, Hng of z plus Bnx is equal to Cng z plus Bny, which is equal to Cnf z plus Bny, and that is equal to Hnf of z plus Bnx. Therefore, for any n greater than 0, we have Hng is equal to Hnf. Now, finally, we show that Hnf is an isomorphism when f is a homotopy equivalence. In other words, topological spaces which are of the same homotopy type have the same homology groups in each dimension. So, we state the theorem formally that if f is a function from x to y and it is known that f is a homotopy equivalence, then for all n greater than equal to 0, Hnf from Hnx to Hny is an isomorphism. So, it is given that f is a homotopy equivalence, therefore, we get a function g from y to x such that g composed f is homotopic to identity and f composed g is homotopic to identity on y, then Hn g composed f is Hn identity on x and Hn f composed g is Hn identity on y. Now, applying the functorial properties of the induced homomorphisms, we get that Hn g composed Hn f is equal to Hn g composed f, and that is equal to Hn identity on x, that is identity on Hnx. Also, Hnf composed Hng is equal to identity on Hny in a similar way. So, Hnf and Hng are inverse of each other and hence they are isomorphisms. In a nutshell, in this chapter we have defined singular homology groups for any arbitrary topological space X. We have also proved certain facts about the homology groups, such as any two homeomorphic spaces must have isomorphic homology groups. Not only homeomorphic spaces, homotopically equivalent spaces also have the same homology groups. In the subsequent chapter, we shall see certain interesting facts about singular homology groups. With this, we end module 3 as well as the chapter 9.